We're now going to take a look at a heat transfer coefficient that is used for heat exchangers, and that is what we refer to as being the overall heat transfer coefficient. So when we're looking at heat exchangers, we're exchanging thermal energy between two different fluid streams. It could be liquid or gas. Typically what we have, we will have force convective heat transfer on one side, conduction through whatever the interface is, and then force convective heat transfer on the other side. And consequently, the overall heat transfer coefficient characterizes all three of those processes. And then you can have other things going on. You can have fins on the heat exchanger that you would then model. You can have fouling going on, which is buildup of deposits, which negatively impacts the heat exchange between the two fluid streams. But what we're going to do, we're going to derive an expression or come up with the expression for the overall heat transfer coefficient. And we're going to begin by looking at a double pipe heat exchanger. So if you recall, this would be a parallel flow configuration. But what I'm going to do, I'm going to label the fluid on the inside as being TA, that's the temperature of the fluid, and I'm going to assume that the convective heat transfer coefficient on the inside is HI. And then for the fluid in the outer pipe, what I'll do there is I will label the temperature TB and H outer, and that would then characterize the force convective heat transfer on the outside of the tube. Now what we're going to do, we want to express this, we're going to use thermal resistances, and so if you recall we looked at that quite a long time ago in the course, but we're going to pull that out now and we're going to use it. So let's draw our thermal resistance circuit and then the different thermal resistance values. Okay, so what we have here, we have three different thermal resistances. One is for convective heat transfer in A, and if we look back, A was being our internal fluid. So that is the internal. Then we have conduction through the wall, and then we have convection on the fluid in the outer pipe. And consequently, we can also write here that if we look at the wall temperatures on the pipe, the inner pipe, it would go from Ti to To, and Q is flowing through. And so let's write out our thermal resistances now. Okay, so those are the three thermal resistances that we have within this system. Now what we're going to do, we're going to combine those together and we're going to solve for the heat flow, very much like what we did when we looked at thermal resistances earlier on. So in this, what we're now going to do, we are going to rewrite the equation. So Q is equal to, and the form that we're looking at here, you'll recognize it is this here, and that's what we've seen before. But what I am now going to do is I'm going to rewrite this in terms of this overall heat transfer coefficient, and we'll have a UA delta T. And in this, what I am doing is I am assuming that the sum of the thermal resistances is equal to the inverse of this overall heat transfer coefficient times an area that we have not yet defined. So U, this is defined as being our overall heat transfer coefficient. And it can be defined either in terms of the inner or the outer area of our double pipe heat exchangers. So what am I referring to? Well, if you look at your wall, this is the inner pipe, and we have, that's the wall thickness. So area inner would be here, and area outer would be there. So it depends if you use your internal or your external radius or diameter of the interior pipe. So what we're going to do we're going to write out two different overall heat transfer coefficients. So those are two different ways of expressing the overall heat transfer coefficient, depending if you use your inner or outer tube area. Now, typical values that we find in heat exchangers are as follows. So you can see a range of values. If we're going through a phase change, it's going to be quite high. If we have water to air, the water will have a higher convective heat transfer. The liquid will have a higher convective heat transfer coefficient as shown there. And then at the lower end, if you have gas, you recall the convective heat transfer coefficients are not as high as a liquid, and consequently the overall value is going to drop somewhat there. So these are numbers that are quite often, well, will be used in the analysis. Sometimes it's given to you, sometimes you're trying to solve it. So a lot of what we're going to be doing when we're doing heat exchanger analysis is trying to estimate a unit's overall heat transfer coefficient. Now, one thing is, let's say you know the value of U, so maybe you've determined this empirically. And if you know the geometry A, things should be good, right? But let's take a look at what our equation looked like. We had Q is equal to UA delta T. So usually we're after the amount of heat transfer. Maybe we know the amount of heat transfer, but that's usually what we're after. But looking at this equation, so let's say you know U, you've determined that, you know your area, and you've been asked to find Q. Well, what delta T are you going to use? And this is what we're going to be looking at in the next segment, in the next lecture actually, because this is not a simple trivial solution. If you even just look at the simple double pipe heat exchanger like this, what is happening is as the fluid is coming through, one fluid stream is heating while the other is cooling, and consequently you are going to have different values of delta T. That is going to be delta T as a function of position. And we did look at this earlier on in the course when we looked at pipe flow, internal force convection, and we came up with an expression. We're going to come up with a very similar expression in the next lecture. But that is in order to enable us to figure out how to express delta T, given that delta T changes as a function of position within the unit. So anyways, that's a bit of an introduction to heat exchangers. We looked at different types of heat exchangers. We looked at how to model the temperature distribution, or at least schematically represented, and then we've just looked at the overall heat transfer coefficient, which is something that we'll carry through when we're doing the analysis. But we're going in the next lecture, we're going to try to figure out how to estimate this value of delta T.